It's a great pleasure to introduce our own Jinyoung Park, who will speak about thresholds. Go ahead.
Thank you so much. And let me first share my screen.
Sure.
Because I'm gonna use my iPad.
So you are at your office as current?
Yes, I'm in my
nice
office.
Congratulations for getting to current.
Oh, thank you so much.
As usual, please everybody mute yourself unless you have something to say.
So yeah, so I wish, I was planning to come a little bit earlier just to have a chat with people, my audience, but oh, I'm sorry, my computer had some problem. Anyway, so
you can have a chat after the recording ends, after 48 minutes from now. You can have some chat. Okay, go ahead.
Okay, so it's my great pleasure to give a talk at this experimental seminar, but unfortunately, my work doesn't have a strong flavor of experimental mathematics. So I hope you please understand if there is not very much experimental math component.
Interesting mathematics is more important than experimental.
Okay, thank you for saying so. And if you have any questions, then please stop me anytime and ask your questions. Just shout out your questions. I'll be very happy to be interrupted. So today I'm going to talk about thresholds and okay. So this is my plan for today. So in this talk, I will introduce the Kahn-Kalai conjecture, which is a central conjecture in probabilistic combinatorics, and then discuss our results related to this conjecture. But we first start with a brief introduction to random graphs, just to begin with a concrete picture in our mind. And also historically, random graph theory was the starting point for our entire story. And later we'll see that the setting of our work is much more general, is something beyond the random graph theory. So yeah, let me first briefly introduce random graphs. So we use GMP for the Erdos-Renyi random graph, and I'm not sure how much the audience is familiar with GMP. So let me just give you the definition. The definition of GMP is this: so we fixed the vertex set. So here I use this bracket n, which means the set of integers from 1 up to n. And here we think n is finite, but this is very large, like 1,000 or 1 million, whatever. So we fix this vertex set, and then we choose each potential edge with probability p independently. So because we have n vertices, so there are n choose two potential edges, and we choose each edge with probability p independently. And in our setting, usually this p is a function of n, so it can be also called as p of n, and this function usually tends to 0 as n tends to the infinity. So in our regime, usually p is something like 1 over n or log n over n. So this is a function of n that tends to 0 as n tends to the infinity. So here I brought some baby example. So what is GMP when n is 3 and p is exactly 1/2? So this means we have 3 vertices and each edge is chosen with probability 1/2 independently. So our sample space consists of those 8 graphs because we have 3 vertices. So we have those 8 graphs. And what's the probability for each graph? The probability for this one is exactly 1 over 8 because each edge is chosen with probability exactly 1/2. So in this case, all of the probability for all of the graphs is exactly 1 over 8. So this is just a uniform distribution. On the other hand, as I said, p is gonna be a function of n, so we can change the value of p. So for example, if p is something very small, like 0.0001, in this case, we can see that this graph is much more likely than this graph. So if p is very small, then the sparse graphs are much more likely than the denser graphs. On the other hand, if p is something close to 1, like 0.999, in this case, the denser graphs are much more likely than the sparser graphs. Does this make sense? Okay, so as we see here, GMP is actually so GMP is not a fixed graph, but this is a probability distribution. So it makes sense to ask questions such as what's the probability that GMP is planar, or what's the probability that GMP is connected, because GMP is a probability distribution. And when we ask this question, we are not really interested in finding the precise probability for those events. Rather, we are interested in what's the typical behavior of GMP. So when we consider the entire sample space of GMP and consider its probability distribution, what type of graph appears with high probability? That's our main concern in the random graph theory. And so because of this, we are going to use WHP, which means with high probability. And when we say GMP does A with high probability, then that means the probability that GMP does A tends to 1 as n tends to the infinity. So do you have any questions about this first page? Okay. Then let me talk about evolution of GMP. One striking thing about GMP is appearance and disappearance of certain properties are abrupt, and this gives us the notion of thresholds. So here I brought a brief picture of evolution of GMP, and in this model, we think of GMP as we add edges one by one at random. So that means at the beginning, we start from n vertices, and there are no edges at all. So this corresponds to P equals 0 because we choose the edges with probability 0. And at the end, when probability is 1, then what we see is GMP is precisely the complete graph with probability 1 because all of the edges are present with probability 1. And then as we slowly increase P from 0 to 1, we view this as we add random edges one by one each time. So in the first step, we have a graph with one edge. In the second step, we have a graph with two edges, etc. Okay, so you can imagine the evolution of GMP from nothing to everything. And here, so one typical example about this phase transition is about maximum size of connected components of GMP. So this says that if n times p is slightly smaller than 1 minus epsilon, so this means p is smaller than 1 over n or minus something. So if p is in this regime, then typical size of the maximum, then typically the maximum size of connected components of GMP is very small, it's just log n. So you see that this is much smaller than n, which is the number of vertices in GMP. On the other hand, if n times p is slightly above 1, then in this case, suddenly we see a giant component whose size is as large as the order of n. So in this case, so in this sense, we can say that p equals 1 over n. This is the threshold for having a giant component. And this change happens very abruptly, just around p equals 1 over n. So this is one typical example that shows this threshold phenomena of the random graph GMP. And there are many other interesting properties which exhibits those threshold phenomena. So naturally, it became a central interest in probabilistic combinatorics to find thresholds for various properties. Okay, so do we have any questions about this slide? Is the motivation clear?
I have a question.
Yes.
What does that notation mean? It's like less than or squiggly.
Oh, that's a very good question. So this means we are not going to care about the constant factors. So if this is, for example, so it can be like 100 times log n. Yeah.
So is it asymptotic up?
So
they have the same limit or up to a constant?
So yeah, it means we only care about the order, and the precise constant depends on the value of epsilon.
Okay, thanks.
Okay. And yeah, thank you for your question. And also this notation means it's in the same order of n. Okay. Yeah, thank you very much for that question. And do we have any other questions? Okay. So in this page, I listed some of the past results on finding thresholds. So I'm not going to read the entire results in this list, but I just wanted to show my audience that finding threshold questions is really well studied and it has a long history. So there are lots of researchers who worked on this kind of problems. And also I wanted to emphasize that if you look at just briefly skim the list, you'll realize that most of the studies have been done mostly for specific properties. For example, what's the threshold for GMP to have like to be connected? Or what's the threshold for GMP to have like long paths or long cycles? So those are very specific properties. But later we'll see that the Kahn-Kalai conjecture like that encompasses all like most of these like subject that we have studied. So it's not just about specific properties, but it's more like a unified bound for the location of thresholds. Okay, so then in this part, let me introduce the notion of thresholds. And let me first start with some basic definitions. As I said, our setting is something beyond the random graph theory. So here we give a general definition which will be a generalization of the things that we considered in the random graph theory. So here, our X is just any finite set. It doesn't have to be a graph. It's just any finite set with like so many elements. And as usual, we use 2 to the X for the power set of X. And we use mu P for the P-biased product probability measure on 2 to the X, which is defined this way. So whenever we have a set inside X, mu P of A is defined to be P to the size of A times 1 minus P to the size of X minus A. And we use XP for the random variable whose distribution is mu P. In easy words, this means XP is a P random subset of X, which means we choose each element of X with probability P independently. And then you can see that for each A, the probability that XP, the P random subset of X, is equal to A is exactly this, because we choose all of the elements in A with probability P, and we want all of the non-elements of A, and the probability that all of the non-elements of A are not present in XP is exactly this. So XP is the P random subset of X. Then, for example, when X is n choose 2, which is the set of edges of the complete graph Kn, in this case, what is XP? It's precisely GMP, because we choose each edge with probability P independently. Or it can be viewed as edge percolation on Kn. So that means if we change our ground set, so instead of taking Kn, we can take just any graph as our host graph, and that gives us edge percolation on the given host graph, whatever graph is given. And also, as I said, X can be anything. So if we consider X as the collection of K clauses from n variables, in this case, we can view XP as the random CNF formula, which is another interesting object in computer science. So I just wanted to give the impression that we are considering something more than the random graph theory. So this is just any finite set. And then we define an increasing property this way. So we say this calligraphic F is an increasing property if whenever we have an object that contains an element in F, then this B is also contained in the same increasing property. And again, in easy words, this means we can't destroy this property by adding an element. So for example, if we consider F to be the property of like being connected, then this is an example of an increasing property, because we can't destroy this property by adding an element, by adding an edge. Another example is to contain a triangle or to contain just any subgraph, because any given subgraph, because again, we can't destroy this property by adding an edge. Is this, are those definitions clear, or do we have any questions? Okay, so because this is a definition page, so I don't want to lose my audience in this definition page. So if there is any unclear definition, then please ask me. Are we good? Okay, thank you. And let me move on. And then let me give you the definition of thresholds. So a well-known fact is that for any increasing property F, unless this is the empty property or the entire property, mu P of F which is by definition, the probability that XP satisfies the given increasing property F. This is continuous and strictly increasing in P. So here I gave some typical picture of mu P of a typical graph of mu P of F. So you can see that if as we increase P from 0 to 1, mu P of F also increases from 0 to 1. And let me not justify this fact, but instead let me give you some example. So for example, let's say we consider GMP, and let's say F is the property to be connected. In this case, if P is 0, then what's the probability that G and P satisfies the given increasing property? Of course, this probability is 0, because when P is 0, no edges are there, so this is not connected with probability 1. On the other hand, if P is 1, then what's the probability that G and P is connected? This is precisely 1, because all of the edges are present, so we have the complete graph, so this is connected with probability 1. So in this case, we are here. And in the second case, we are here. And this fact says that as we increase P from 0 to 1, mu P of F also increases from 0 to 1. And because this function is continuous, so there must exist something called PC of F, for which mu P of F is exactly 1/2. And this PC of F is called the threshold for F. And again, intuitively, the meaning of the threshold is this: if we are below the threshold, then it is very unlikely that our random variable XP satisfies the given increasing property F. On the other hand, if we are above the threshold, then it becomes very likely that our random variable XP satisfies the given increasing property F. So really, the threshold is where this phase transition happens. Okay? And if you are familiar with the traditional random graph theory, then probably to you, the meaning of the threshold is this. So Erdos and Rennie, they defined a threshold function for a sequence of increasing properties in this way. Let me not talk about this definition, but if you're curious, then I can tell you that if we define the threshold in this way, then this PC of Fn is always an Erdos-Rennie threshold. And we can prove this, we can justify this using a theorem of Bolobashi and Thomason. So anyway, because of this red comment, from now on, we're gonna use the definition of the threshold instead of a threshold function of Erdos and Rennie. Okay. So are there any questions about the notion of thresholds? Okay, let me move on. So, and there are two very interesting directions of study of thresholds. The first direction is what we do. So we are interested in finding or studying the location of thresholds. So where is the threshold, or what function is a threshold function for the given increasing property? And as we saw before, historically, most of the interesting work was on thresholds for specific properties, like containing, long paths or containing a Hamiltonian cycle. And the Kahn-Kalai conjecture suggests a general bound on the location of thresholds. So briefly, let me just give you a preview of this conjecture. So here, let's say an increasing property F is given, and we are curious about where is PC of F. So this one is in between 0 and 1. And in general, when an increasing property is given, finding PC of F is a very hard task. But there is another parameter which we'll call PEF. I'm going to introduce this later. And this PE of F is usually easy to compute, and this is always a lower bound on the threshold. And then the Kahn-Kalai conjecture says that actually PC of F is not very far from this trivial lower bound. So they said that PC of F is actually bounded above by PEF times a tiny error term. So if this conjecture is true, which we know that this is true. So this conjecture says that we can predict the location of the threshold using this easy lower bound. So this is a very strong conjecture or theorem. And the second direction of the study of thresholds is called sharpness of thresholds. And there are also many interesting questions and results there. And basically, simply speaking, what this means is how steep this graph is. In other words, let's say this is epsilon and this is 1 minus epsilon, and sharpness concerns what's the length of the interval from here to here. And what's interesting is in this line of work, most of this interesting work, they are based on Fourier analysis. So to prove the Kahn-Kalai conjecture, people did try to use Fourier analysis, but it seems none of them worked so far. So instead, the proof of the Kahn-Kalai conjecture uses a very combinatorial approach, which hopefully we can reach at the end. Okay, so any questions so far? Is it okay? Is there anything? Okay.
Is it obvious that it exists all the time? That this threshold exists? Is it obvious?
You mean threshold?
Yeah, the existence.
Oh, yeah, of course, because of this. So we know that mu p of f is always continuous and strictly increasing. So by the intermediate value theorem, there must exist the threshold for any increasing property.
Thank you.
Okay, that was a good question. Do we have any other questions? Okay, then let me move on to the Kahn-Kalai conjecture. So as I said, this is a very strong conjecture. And so even the authors of this conjecture wrote in their paper that it would probably be more sensible to conjecture that it is not true. But it turned out this conjecture is true. And in this section, I'm going to introduce 3 examples, which shows the motivation behind the Kahn-Kalai conjecture. And in all of those examples and in the conjecture itself, the fundamental question is what drives the threshold? So what determines or what affects the location of the threshold? That is the underlying question in this conjecture or in the examples. So in the first example, so here we are considering GMP because the motivation of the Kahn-Kalai conjecture was the random graph theory. So all of the examples will be from the random graph theory. So in this example, our XP is GMP. We consider Erdos-Renyi random graph. And the increasing property is to contain a copy of H, where H looks like this. So H has 4 vertices and 5 edges. And then the question is, what's the threshold for GMP to contain a copy of H? And if you have taken the probabilistic methods in your course, then you know the answer. So let me start from the beginning. So we are curious about the number of copies of H in GMP. And because GMP is a random variable, as we discussed at the beginning, so the number of copies of H is also a random variable. And moreover, this is a numerical random variable. And whenever we want to understand a numerical random variable, the very first thing that we want to check is its expectation, right? So checking expectation is a very natural approach to understand the number of copies or the existence of H in GMP. So if we compute the expected number of copies of H's in GMP, then if we ignore the constant factor, it becomes n to the 4 times p to the 5. This n to the 4 is the number of potential copies of H's in the complete graph, because we have n vertices, so there are roughly n choose 4 many potential copies of H. And so this p to the 5 is the probability for each copy of H to exist inside GMP, because H has 5 edges. So the probability for each edge to exist is exactly p to the 5. And we don't care about the other edges. We just want the edges of H to exist. And the probability for that is p to the 5. And you see that this quantity tends to 0 if p is much smaller than this. and it tends to the infinity if p is much larger than this. So in this sense, we can say that the threshold for the expectation is in the order of n to the -4/5, because this is where the phase transition happens in terms of the expectation. And once we have this, this computation gives us this trivial lower bound on the threshold. This is because if the expectation tends to 0, then typically we don't, if the expectation of number of copies of H tends to 0, then that means typically we do not see any copies of H in GMP. So that means because of the definition of the threshold, that means the threshold for having a copy of H must be at least as large as n to the -4/5. So this is a lower bound on the threshold. Then but it turned out, actually, we know that the truth is the threshold is actually in the same order as n to the -4/5. This uses the second moment method. We can show that the variance is very small, so the number of copies is concentrated around its mean. So we use that, but let me not go into the details. But anyway, what this example shows us is, usually the threshold is hard to compute, but in this case, the threshold is equal to the threshold for the expectation. So the easy computation of the expectation actually predicts the right value of the threshold up to a constant factor. So here we can dream that, maybe this easy expectation computation predicts the location of the threshold. Okay, so keeping this in mind, let me move on to the second example. In this example, we consider a little bit different graph, H tilde. So H tilde is, I hope you noticed that basically this one is H with a little tail. I hope you remember this. And question is the same. What's the threshold for GMP to contain a copy of this H tilde? And in the previous example, we learned the lesson that, expectation computation tells us something about the location of the threshold. So we do that. So if we do this expectation computation, then we have n to the 5 times p to the 6 this time, because H tilde has 5 vertices and 6 edges. So this expectation tends to 0 if p is much smaller than this, and it tends to the infinity if n is much larger than this. So in this sense, we can say that the threshold for the expectation is n to the -5/6. So this tells us that this value is a trivial lower bound by the same reason. And the question is this n to the -5/6 the truth for the threshold? But in this case, again, if you have taken the probabilistic combinatorics course, then we know that the answer is no. It turned out the truth is n to the -4/5. Why is this? So this says that, so here n to the -5/6, and this is the threshold for the expectation. And we know that if we are below this value, then there's no H tilde with high probability. But it says that even if we are here, n to the -4/5, even if we are here, we know that the expected number of H tilde is very large. But we know that still H tilde is not contained in a GMP with high probability. Why is this true? This is because, so what is n to the -4/5? This is the threshold for H, if you still remember. So this means if we are below n to the -4/5, then typically there is no H. And because H is a subgraph of H tilde, so if there is no H, then of course there's no H tilde. So the expectation computation of H, which is a subgraph of H tilde, gives us a better lower bound than the expectation computation of H tilde itself. So we get 2 lessons out of this example. The first lesson is just computing the expectation of H tilde itself is not enough to predict the right threshold. On the other hand, the second lesson is if we consider the right subgraph of the given graph, then its expectation computation gives us the right threshold. And this lesson is generalized by Renyi and Bolobash. So they said that roughly for any fixed graph H, the threshold is equal up to a constant factor to the threshold for the expectation of the densest subgraph of H. So basically, it tells us that as long as we consider the densest subgraph of H, its expectation computation gives us the right value of the threshold of the constant vector. Okay. So yeah, so basically we are done with any fixed graphs because of this Bolobash result. So then what's the next example that we want to consider? So we are moving beyond the fixed graph. So we are moving to a growing graph. So in the next example, we consider a perfect matching. Oh, by the way, what is a perfect matching? That means it looks like this. So this is a disjoint union of edges that contains all of the n vertices. This is the meaning of a perfect matching. And the question is the same. What's the threshold for GMP to contain a perfect matching? Oh, by the way, do we have any questions about the first two examples? Okay, then let me move on to this example. So in this example, we learned some lessons. We learned the lesson that if we compute the expectation, that gives us a lower bound. And in this case, if we compute the expected number of perfect matchings in GMP, then let me skip the computation, but we know that it's roughly this value. So we see that if P is much smaller than 1 over n, then this tends to 0. And if P is much larger than this, then it tends to the infinity. So a trivial lower bound is PC of F is at least 1 over n. Because if we are below 1 over n, then typically there is no perfect match. So we can ask a question like, that is the threshold just equal to 1 over n? And it turned out the answer is no. The truth is the threshold is log n over n. So you see that here we have this log n gap between the actual threshold and this trivial lower bound from the threshold for the expectation. And unlike in the previous example, we discussed that as long as we look at the densest subgraph, then its expectation gives us the right threshold. However, when you look at a perfect matching, there is really no like densest part. They all look the same, even if we consider a subgraph of a perfect matching. So indeed, this 1 over n is the right threshold for the expectation, whatever subgraph we consider. And so that means here we do have this log n gap between the expectation, the threshold for the expectation and the actual threshold. So then, so this is very frustrating. So what do we do? Or do we we never give up. So the next thing that we want to do is to try to understand where this log n gap comes from. So it turned out, so this is where we are. So we want to understand why we have log n over n. And okay, so our question was, what's the threshold for a perfect matching? And we checked that the threshold for the expectation is 1 over n, but the actual threshold is log n over n. But it turned out, actually, this log n over n is another trivial lower bound on the threshold. This is because of the fact that if P is much smaller than log n over n, then typically GMP has an isolated vertex with high probability. And because we are talking about a perfect matching, so that means if there is an isolated vertex, then of course there is no perfect matching. So the existence of an isolated vertex pushes up this trivial lower bound from 1 over n to log n over n. Okay, is this clear? Yeah. And so yeah, so this fact is because of the coupon collector problem. I don't know if I want to explain this. So let me just skip this part just to save time. But yeah, but this blue fact comes from has a relationship to the coupon collector problem. But let me not talk about this here. So here, let me introduce just one more example. So now we are moving from GMP to a random hypergraph. So let me define what is a random hypergraph. So from now on, X is not n choose 2, but n choose R, which means our ground set is n, the n vertices, and n choose R means we consider all of the R tuples. So n choose R is the collection of all of the R tuples on n graphs. So then in XP, and XP means we choose each R tuple with probability P independently, and this is called random R uniform hypergraph HRNP. And then we ask the same question. When R is larger than 2, what's the threshold for HRNP to contain a perfect matching, where a perfect matching here means a disjoint union of R tuples that contains all of the n vertices. And of course, here we need this silly assumption R divides n, but let me not worry about it. But so yeah, again, we are considering the existence of a perfect matching, and this problem was like notoriously hard. So this problem was suggested by Elie Shamir. So this is called Shamir's problem, and this problem was open for about 30 years. So this was notoriously hard. But again, at least we can, but here, if R is 2, then we consider a like ordinary random graph. And that case was proved already by Erdős and Renyi in 1966. So somehow when R is larger than 2, then the problem gets much, much harder. And basically this is because when R is strictly larger than 2, then there is no analog of Hall's theorem or Tutt's theorem for the existence of a perfect matching. Anyway, so it's hard when R is larger than 2. So just for concreteness, let's consider R equals 3, and let's apply our strategies that we learned from the previous examples. So if we just consider the expected number of perfect matchings in HRNP, then this expectation gives us this value. So from here, we can compute that the threshold for the expectation is n to the negative 2. On the other hand, if we consider the lower bound from the coupon collector problem, then we have this better lower bound, which is log n larger than this threshold for the expectation. And it turned out the right threshold is log n over n squared, which is famously proved by Johansson, Kahn, and Wu in 2008. So here in this answer, we see this log n gap again. Okay, so are we motivated by this log n? Because eventually the conjecture says this. So let me summarize what we have seen so far. So our fundamental question was, what drives PC of F, the threshold? And in the previous examples, we saw that we have some trivial lower bounds on the threshold. From the first 2 examples, we saw that the threshold for the expectation gives us a trivial lower bound. And from the last 2 examples, we saw that the existence of coupon collector, the isolated vertices, that's what I meant by coupon collector. The existence of isolated vertices pushes up the first lower bound by log n. And historically, in many, many interesting cases, the main task is to find a matching upper bound. And then the Kahn-Kalai conjecture says that roughly for any increasing property, the threshold is at most log x times the expectation threshold. So this indeed says that whenever we want to find PC of F, we know that the expectation threshold gives a lower bound, and actually expectation threshold times log x, where this log x is a teeny tiny compared to, like, usually this is very tiny term. And this conjecture says that we can trap the location of the threshold in this small window. Okay, so as I said, this is a very strong conjecture. For example, this immediately implies historically very hard questions like threshold for perfect hypergraph matchings, which we just saw. So this is how the conjecture works. For this one, we've seen that the value of the expectation threshold is n to the negative r minus 1. And if we apply the Kahn-Kalai conjecture, then we have this upper bound, log n over n to the r minus 1. And we know that this upper bound coincides with the lower bound from the isolated vertices or coupon collector behavior. So this is how we apply this conjecture to get the right threshold for a very hard increasing property. And another famous example is threshold for bounded degree spanning trees, which is called tree conjecture. yeah, so this one was also open for a long time and recently proved. And we can, so this is another application of the Kahn-Kalai conjecture. And because I don't have so much time, so I don't know what to do, but I want to say this. So actually those two problems on the screen now, they are the motivation for the Kahn-Kalai conjecture. So when you compare the years, you can see that the Kahn-Kalai conjecture came before this Johansson or Montgomery's result. So at the time the Kahn-Kalai conjecture came out, those two questions were still notoriously open. And when you have some very hard problems and you don't know what to do, then what do? One thing that we can do is to make the problems even harder. So they just made this conjecture which immediately implies those hard questions. And it turned out this like generalization was the right thing to do in this case, because yes, so we know that, I mean, Johansson paper is very, very hard. And also Montgomery's paper is also very hard. So Johansson they received the Fulkerson Prize out of this work, and Montgomery's paper is like 70 pages. But the proof of the Kahn-Kalai conjecture, the entire paper is just 6 pages, and the very last page is only for the references. So the actual math contents is just 5 pages. And the first 2 pages are for the introduction. So real math part is really short. And yeah. Okay, so I think I advertised enough, but I forgot. I mean, I haven't mentioned what's the definition for
that your proof is self-contained, or it relies on deep previous results. The 5 page, the 5 page that you mentioned of your proof, is it self-contained or it relies on previous heavy?
No, it's no, it's self-contained. We do not rely on anything. Yeah, the entire self-contained proof is just within 5 pages.
Wow, nice.
Yeah. Okay, yeah, thank you for that question. And yeah, so maybe I can give you the definition of the expectation threshold and finish this talk. So the problem is, as I said, our setting is much more general. So we are not with the random graph setting, and F is just any abstract increasing property, and there's no symmetry at all. It's just anything arbitrary. So in this setting, it's not clear whose expectation we want to compute. So we need a careful definition for the threshold for the expectation. And this is how we define the expectation threshold for an arbitrary increasing property. The first observation is this. So this is about a lower bound on the threshold. We know that Q is a lower bound on the threshold if there exists a collection inside the power set, inside 2 to the x, that satisfies the following 2 properties. The first property is G covers F, which means whenever we have an element in F, we can find an element in G such that A contains B. And this cover actually corresponds to the subgraphs. So this means if we consider H tilde, if you still remember what this is, in this case, so H tilde is covered by H. The second one corresponds to expectation computation. So it says that this quantity is at most 1/2. And then what is this? Q to the S is precisely the probability that S is contained in XQ. So this entire sum corresponds to the expected number of S's contained in XQ. So the second one corresponds to the expectation computation. And this observation says that if the expectation computation of a cover is small, then that Q gives a lower bound on the threshold. So this is very easy to justify, but let me not justify this observation, but instead, let me give you an example that shows the connection between this observation and the previous example that we considered. So in example 2, we considered this increasing property F to contain a copy of H tilde. And here, one obvious choice for a cover is all of the copies of H tildes, right? Because if we choose G1 this way, then G1 covers F, because every H tilde contains at least one H tilde. And And then this computation in number 2, this one is exactly the expected number of H tildes in G and Q. And we did this computation, and then we got that Q is at most n to the negative 5/6. So this gives us our first lower bound, if you still remember the computation. But we saw that we can do better. If we choose G2 to be all of the copies of H's, then still this is a cover, because every H tilde contains at least one copy of it. Sorry, if a graph contains H tilde, then it must contains H. So G2 is another choice of cover. And then we saw that this expectation computation gives us a better lower bound. This is what we saw in the second example. So what we see is whenever we have a cover, we have a lower bound on the threshold. And then the natural definition for the expectation threshold is the maximum among all of the lower bounds. So whenever we have a cover, we have a lower bound, and we consider all of the lower bounds, and then we choose the maximum one. And that gives us the definition for the expectation threshold. And then now the statement of the Kahn-Kalai conjecture is this. This is a rigorous statement. It says that there exists a universal constant K. So K comes first. This is a fixed constant, and it doesn't depend on anything, such that for every finite set X and increasing property F, PC of F is at most this constant times the expectation threshold times log of the size of the universe. And then how big this K is. So in our computation, we didn't care about optimization. So in our paper, it's about 1,000. But recently, I heard that this constant is improved to like 11 or something. So this is very small. So let me stop my talk here. So I'm glad that I could deliver the statement of the Kahn-Kalai conjecture. And thank you very much for your participation.
Let's applaud for a great talk. To observe the 48-minute axiom. Now we have 2 minutes for formal questions. And after that, we are welcome to stay and ask Jinyoung for informal questions. Any formal questions before the recording ends?
I might have one.
Yeah, go ahead, sir.
So can you give some intuition why we have this extra factor of walk n, but not walk square n or something like that?
So, okay, because, so as I said, we have 2 kinds of lower bounds, right? The expectation threshold and the coupon collector or isolated vertices that pushes up log n. But people couldn't think about, is there any other thing that pushes up those 2 trivial lower bounds? And there wasn't. So it was natural, or it was very bold to conjecture that, oh, this log n is the truth, because we don't see anything else to push us up these lower bounds more. And then it turned out that was the truth. Oh, so yeah, sorry, I think I didn't introduce my theorem. Yeah, that conjecture was proved recently by myself and Huy Pham. Yeah.
It was very impressive. So the proof is easier than the special cases that were proved before.
Oh, what are the special cases? Yeah.
No, it implies some previous results, right?
Yeah, of course, it's much easier. As I said, the proof itself is like 2-3 pages, and it's self-contained. Yeah, it's very short and easier.
So that's the Polya principle. The more general, the easier to prove. But you have to find the right approach, of course.
And also, what's impressive is so this is very combinatorial proof, but it doesn't rely on so the most advanced technique that is used in this proof is Markov's inequality. So there's nothing beyond that.
So it's more elementary than the previous ones. Yeah. But thanks so much. Robert, please stop recording. But everybody, people are welcome to stay and keep asking Jinyoung questions.